Electricity. It's literally powering everything around us right now. But for a lot of us, it just feels like this invisible, super technical magic, right? Well, today, our whole mission for this explainer is to totally demystify it. Oh, I am so ready for this. Electricity can be incredibly frustrating if you're trying to wrap your head around it for the first time. So, getting a really solid, visual, mental model is going to be an absolute game changer.
Okay, so to kick things off, quick question for you. What do complex electronics and your everyday garden hose actually have in common? I know, it sounds like a weird setup to a joke, but the answer is basically the ultimate anchor analogy that's going to make all this complex physics instantly relatable.
Exactly. So here's the game plan. 1, the water pipe analogy. 2, voltage as the pressure. 3, current as the flow. 4, resistance as the bottleneck. And finally, 5, we'll put it all together with Ohm's law. Let's dive right in.
All right, section 1, the water pipe analogy.
So at its core, electricity is really just the invisible flow of electrons through a wire. But since we obviously can't see that happening, we're going to use plumbing. If you just imagine electrical wires as hollow pipes and the electrical charge as the water flowing through those pipes, I promise everything else is just going to click right into place.
Moving on to section 2, voltage, the pressure, basically the big push in a circuit.
Right. Okay. So if you look at a textbook, the definition of voltage says it's, quote, the difference in electric potential or electromotive force between 2 points. Now, I got to ask, what on earth does electromotive force actually mean in plain English?
Yeah, it sounds way more complicated than it actually is. In plain English, voltage is just the push. It is exactly like water pressure coming from a big water tank. The more water you have in the tank, or the higher up you put it, the stronger the pressure pushing down at the bottom of the hose. In electricity, that difference in potential, that pressure, is what physically pushes the charges through the wire. It's measured in volts, but seriously, whenever you hear the word voltage, just think pressure.
Okay, makes total sense. And if voltage is the pressure pushing the whole system, that smoothly pivots us right into section 3, current, the flow, the actual physical movement of the electrons themselves.
Exactly. Current is the rate at which those electrons flow. But hey, we actually need to clear up a massive misconception right now. A lot of people think electrons zip through wires at lightning speed. They don't. They actually migrate incredibly slowly. We're talking maybe a meter an hour.
Wait, really?
Yeah. But because the wires are completely jam-packed with them end to end, the second you flip a switch, they all just move together at the exact same time, kind of like a massive line of soldiers marching in perfect step.
Oh, that soldier's marching visual is so good. And bringing this back to our water analogy, if voltage is the pressure pushing the water, current is simply the flow of the water itself. But instead of measuring, say, gallons of water flowing past a point every second, we measure the flow of electrical charge in amperes, or just amps. And speaking of measuring that flow, get this. 1 ampere is defined as 1 coulomb of charge passing a single point per second. Now, a coulomb is exactly 6.24 quintillion electrons.
No way.
Yes, that's 624 with 16 zeros after it. That many electrons passing by a single point in the wire every single second just to give you 1 single amp of current. It's honestly mind-blowing when you really think about the scale.
It really is. Which naturally leads us to ask, what happens if something gets in the way of all those billions of marching electrons? That brings us to section 4, resistance, the bottleneck, the opposition to the flow. Nailed it! That is exactly what resistance is. It's the opposition to electron flow, and we measure it in ohms. You see, no material is perfect, right? So there's always going to be some inherent friction slowing down the current. Sometimes we even add specific components to the circuit, literally called resistors, just to intentionally slow that current down and protect the more sensitive parts of the electronics. Which brings us right back to the good old garden hose. Resistance is exactly like stepping on the hose or forcing the water to squeeze through a tiny, narrow pipe. The tighter you pinch that hose, the harder you make it for the water to flow. Simple as that.
Precisely. And a really crucial point for anyone doing hands-on stuff. You can physically measure that pinch using a tool called a digital multimeter. But, and this is a huge but, you can only measure resistance when the component is completely unpowered.
Ah, right, because of how the meter actually works.
Exactly. The multimeter sends its own tiny, safe little voltage into the component to test how much current flows. If the circuit was already plugged in and powered, all that extra voltage would totally mess up your reading, and you'd probably fry your meter in the process.
Okay, good safety tip for sure.
So I get how one single resistor acts like a pinch in the hose. But how do multiple resistors behave when they're together in a circuit?
Think of it like highway traffic. If you wire resistors in what's called a series circuit, meaning one right after the other on the exact same path, it's basically like a one-lane highway with multiple broken-down cars. Every stuck car you add makes the traffic jam worse, so the total resistance just adds up.
Right, that makes sense.
But in a parallel circuit, you're actually giving the electrons multiple different paths to take. It's like building a whole second road right next to the highway. Even if that second road has a stuck car on it too, just the fact that there's another path available means more total cars can get through. So counterintuitively, in parallel, the total resistance actually drops.
That's a great way to picture it. Which brings us to the grand finale, Section 5, Ohm's Law, putting it all together. This is where voltage, current, and resistance all combine into one legendary equation.
Yeah, this is where you see how incredibly intuitive Ohm's Law really is. The formula is V equals I times R, or voltage equals current times resistance. Think about it practically. If you increase the voltage, so you pump up the water pressure, the current, the flow, naturally goes up. But if you increase the resistance, you squeeze the hose tighter, the current drops. It's just a perfect logical balancing act.
Okay, let's do a super quick recap just to completely lock in this mental model. Voltage is your push, the water pressure. Current is your flow, the gallons per second of those marching electrons. Resistance is your bottleneck, the pinch in the hose. And Ohm's law is the ultimate rule that binds all three together. Honestly, if you understand these four concepts, you have grasped the absolute foundation of all electronics.
Absolutely. Which leaves us with this final kind of crazy thought. If these three incredibly simple water pipe rules govern literally every single electrical circuit, just think about the sheer scale and complexity required to combine those basic concepts into the device you're using for this explainer right now, right? Millions and millions of microscopic pathways, all constantly balancing pressure, flow, and bottlenecks just to process information in real time. It really is a fascinating world. Thanks so much for learning with us today.